I've been living the AI dream for 40 years. We're pretty sure the universe is computational all the way down. Take the computation seriously because it's the way the universe is actually built. A neural net is something that is good at kind of broad but shallow kinds of things. A computational system is good at deep but less broad kinds of things. Yes, there are many threads of history. The important thing is those threads of history both branch and merge. We're limited. We have finite minds. We have finite brains that just can figure out a limited amount of computation.
I guess where I kind of wanted to start is in one of your more recent interviews. You kind of have this idea. You said that was very interesting how you can take these neural networks and with deep learning kind of bash them until they learn something complex. And it was kind of like a very interesting sort of a fairly recent discovery. And you tied it to biology and how evolution works. And maybe let's start there because I think that kind of ties a lot of this together.
Right. I mean, I first started playing with neural networks at the beginning of the 1980s. Couldn't get them to do anything interesting. About the same time, I got curious about how does biological evolution manage to produce all the amazing things it manages to produce, including us and so on. And the question was, if you had some simple rules by which a system could operate, and then you keep sort of mutating those rules, could you get the thing to do really interesting stuff like we see in biology? I didn't manage to make that work back then. Okay, so now we fast forward several decades. 2011, 2012, people discover that with neural nets, if you kind of bash them hard enough, if you give them enough training, they will learn things like how to do image recognition. Wasn't obvious to anybody that was going to work. It was something that is sort of a scientific discovery, scientific breakthrough in a sense, that was surprising. So then a couple of years ago, I started thinking about the biology problem again. And I wondered, if you take these very simple computational systems, I'm just dealing with these cellular automaton systems, which are just rows of cells that have simple rules that determine the color of a cell based on the colors of previous cells on the step before. It's like, could you mutate the rules for those things? And could you sort of bash it hard enough that it would succeed in kind of learning how to do things that are biologically useful? And turns out the answer is yes. And so what you find there is you're kind of mutating the rules. You're trying to get it to, for example, be a little idealized organism that lives as long as possible, let's say. Question is, how does it do it? And the answer is it makes these incredibly elaborate patterns that just happen to live a long time. If you say, can you explain the mechanism by which that works? Not really. It just does this very complicated stuff which happens to succeed in living a long time. And I think that's a lot of what we see in biology. When we see a biology textbook or something, and it's full of all this incredible detail about how we work or how biological systems in general work, we're seeing a reflection of the same phenomenon of just that this essentially computational process that manages to happen to work. And that's what biology kind of captured and has been making use of for the last, depends on what the system is, a few billion years or whatever it is. And I think it's the same kind of thing in machine learning, that when we are training a neural net, what's happening is we're making use of this kind of underlying computational capability. We're discovering that there is a way to get that sort of underlying computational capability to do this thing that sort of happens to work to achieve what we want. I mean, one might have imagined that what one's doing when one trains a neural net, when biology is doing natural selection, that it would be discovering some understandable mechanism to get the system to do what it does. But I don't think that's what's happening. Instead, I think what's happening is that it is searching through this sort of computational universe of possible systems and finding one that happens to work. And most of the systems that happen to work do it in a very ornate, complicated, non-explainable way. And that's what we're seeing both in biology and in machine learning. So when you say, in machine learning, how does it work? How does that neural net manage to recognize the cat from the dog or whatever? The answer is there isn't really a good narrative answer. It's very unsatisfying from a sort of science point of view, because science tends to be kind of the story of how do we make sort of a human understandable narrative about how some aspect of the world works. And to say, well, it just happens to work is a rather unsatisfactory conclusion, but it's not. It's something that, it just that is what's going on. It's not something where we can say sort of mechanistically, this thing produces that thing, and we can kind of tell a story about how this neuron affects that neuron, and eventually it says the answer is a cat or something. So I think that's and kind of the underlying phenomenon in all of this is this thing I call computational irreducibility that I kind of realized was a thing now 42 years ago. It's amazing. Um, the and kind of what led to that discovery was the following thing. So I was interested in what do extremely simple programs typically do. When we think about programs, we usually think about these things. We write some program for some particular purpose. It does what it does in some sort of understandable engineered way. But I got interested in sort of the basic science question. If we just imagine some program that's defined by some incredibly simple set of rules, let's say, have a line of black and white cells. We just say the next cell down the page is going to be determined by some fixed rule in terms of the colors of the cells above it, let's say. We just keep running that rule. You might say, oh, it's a very simple rule. It will only be able to do very simple things. That's what I thought. So back in beginning of the 1980s, I decided I'll actually do the experiments, do the computer experiments, see what actually happens. The results were incredibly surprising. It took me a couple of years to kind of come to terms with what I'd actually seen, which was even though the rules are really simple, the behavior that you can get can be really complicated. And that's a sort of fundamental fact of the computational universe. It's very different from our usual intuition about how engineering works. We usually tend to think if we want to make something complicated, we have to go to lots of effort and have very complicated plans to make that complicated thing. But what happens in the sort of computational universe of possible programs is out there in the computational universe of simple programs, there are lots that just spontaneously do very complicated things. And then the kind of the one of the consequences of that is, okay, if you see the program, can you predict what it will do? And what you realize is it's kind of irreducibly difficult to do that. Yes, you can run the program step by step and see what happens, but you can't in general expect to kind of jump ahead and say, okay, given the program, I can just say, I know what the result is going to be. So that phenomenon of the fact that the only way to know what's going to happen is basically to follow each step and see what happens, that I think turns out to be a really important phenomenon. That's sort of the foundation of a lot of kinds of ways to think about science, conclusions about technology, and so on. And that's the thing that one is both seeing as a limitation in, oh, can we understand how the neural net works, let's say, and it is also a strength in the sense that when there is a computation that is irreducible, that computation is in a sense achieving something. If it was the case that we could just say, we see what's going into the computation, we can just jump ahead to the answer, we wouldn't have to do the computation to see what happens. It's the fact that there is this kind of irreducible effort of computation that's going on. That's the thing that we're leveraging both in biology and in machine learning to do the kinds of things that we do. We're kind of using these lumps of irreducible computation, putting them together in ways that turn out to be useful for the purposes that we have. That was a very long answer to
Yeah.
what seemed
Oh,
like a short question, but
Oh no, this is perfect, and it's a great, I think, kind of opener for everything that we're going to dive into. So, computational irreducibility for people that I almost think of it as like you have to watch the movie from beginning to any given point to see what happens. You can't just predict by some model what happens, so you have to play it out. But kind of what we were talking about with how these complex learnings happen from bashing a neural network, or how fitness functions form from evolution, as well as everything that you started at the beginning of your career kind of discovering. It always seems like it's an emergent property of physics or reality, or how nature works. Is that fair? Would you agree with that?
well, it's not a feature of nature. It's an abstract thing. I mean, these programs are not things. The fact that they are relevant to the natural world is a non-trivial, independent scientific fact. The the idea that when you set up this abstract program, it will do this kind of thing, that's not a feature of nature. That's a feature of sort of the abstract world, so to speak. I mean, I think the thing when one's talking about sort of how the thing to understand about both biology and machine learning is we're kind of mining the computational universe for these lumps of irreducibility. And when we make something that is going to be useful to us, we're doing it by sort of putting together these blocks of irreducibility. So the way I tend to think about it, you've got a problem you're trying to solve. You're trying to, let's say, build a wall. And you're trying to do that with sort of machine learning methodology or biology methodology for that matter. One way you can build the wall is say, I'm going to make a bunch of bricks. I'm going to do this very engineering oriented thing. I'm going to organize the bricks in this very organized way so I can understand what's going on. I build up the wall. But the alternative is I'm going to look around and see a bunch of rocks lying around, and the rocks are all kinds of weird shapes. But I'm going to discover that I can fit those rocks together to achieve the objective I want to achieve, which is to build the wall. And that's, I think, what's happening both in biology and in machine learning, is that we're making use of these lumps of irreducibility, which happen to fit together to do the things we want. Now, if the things we wanted were incredibly sort of sophisticated and precise, we probably wouldn't be able to do that. In biological evolution, if every organism, as soon as it was born, was able to, solve some elaborate mathematical problem and do this and that and the other thing, organisms just wouldn't survive if that's what they had to do to survive. It's the fact that the fitness that you need to survive in biology is a much mushier thing. Similarly, in machine learning, it's a question of, well, what precisely are you trying to do? If you were trying to get the machine learning system to precisely define this mathematical thing about cats versus dogs, you wouldn't be able to learn that. But what it is that the thing, your actual distinction you're trying to learn is sort of the human-like mushy distinction of a cat picture versus a dog picture. And that's something that sort of these lumps of computational irreducibility are strong enough that you can put them together in such a way as to achieve that. I mean, it's something we see now in kind of machine learning systems. People say, well, can it do these precise computations? The answer is no, not really. It's good at doing these things which are useful for many human purposes, where you were sort of putting together these lumps of irreducible computation to build it up to doing something that's useful to us, like producing an essay that's roughly right or something like this. But when we say, make this very precise thing that's a tall tower of sort of precisely made bricks, that's not the kind of thing we're getting either in machine learning or in biology.
So maybe you could help me understand some of these concepts, how they connect from the physical world to the mathematical world. So to me, I can imagine something like Conway's Game of Life. I can see simple rules turning into complex things. I can even imagine agents that become sort of black boxes based on the dimensionality of their vectors. But I also can see this sort of pattern in chemistry, in the real world, maybe building up to biology and potentially even consciousness. But it seems hard to bridge the two gaps. And like the word quantum sort of seems to come up. But can you tell me, like, how are you thinking about the difference
There are
between
lots of different concepts that you brought in.
how, like from the
So,
math to the real world?
well, let's see. I mean, okay. To avoid one confusion, okay? So, the Conway Game of Life thing, two-dimensional cellular automaton, people often say, oh, I mean, it is actually a pretty good example of simple rules doing complicated things, but most of what people think about there is building kind of engineering structures, like make this glider that moves across the screen, make this thing that is this sort of engineering achievement. That really isn't the phenomenon we're talking about. The fact that you can make kind of engineering understandable things out of something is sort of the opposite of what we're talking about. What we're talking about is kind of what computation does in the wild when you're just letting it do what it does, which is what we see in the natural world. The natural world does what it does and does a lot of complicated things. When we try and harness the natural world for technology, we are trying to not have that random fluid that's flowing in this very complicated way. We're trying to have the thing go through a pipe and have water come out the other end type thing. We're constraining it to have some simpler form that is useful to us. Now, in terms of, what's the relationship between kind of the abstract kind of, what can be done computationally with things you can think about in terms of bits and so on, and what happens in our physical world? Well, that's a very interesting question. That's a deep rabbit hole about which I have spent some large amount of my life thinking. So let's dive into that rabbit hole. So, the first sort of question is, um, how do we model the physical world? How do we? First thing to understand is what science has concerned itself with doing is taking what actually happens in the natural world and trying to make some kind of abstracted model of what's going on that allows you to say, okay, as a human, I understand there are these laws of physics, and I can describe those laws of physics. When I look at the natural world, it follows those laws of physics. So kind of science is about making this abstracted description of what we observe the world to be doing. So then the question is, well, what kind of abstracted description is useful for understanding how the world works? And what has been sort of the tradition in science is, let's capture some particular feature of the natural world, the particular orbits of planets or something like this. And let's say, how do we understand that part of how the natural world works? We've ended up with these scientific models, which are various kinds of approximations to how the natural world works, where we pull off some particular feature and try and describe that in a way that we humans can understand. A much more challenging question is, what is the ultimate machine code of the universe? Is there some way we can describe everything? Is there some way where, in principle, we can say this is how everything works? Not some approximation of some piece, but the everything story, so to speak. And that's a thing which, to my considerable surprise, we made extremely great progress on in the last 6 years or so. And I mean, to tell that story, it kind of, the story kind of starts in antiquity. And, one of the big debates of antiquity is the universe, in scientific debates, is the universe discrete or continuous? Is it made of atom-like things, or is it kind of a continuous flow like water or something? And that question was not resolved for a couple of millennia. By the end of the 19th century, sort of the discovery was made that matter is discrete. Matter is made of discrete atoms and molecules. And then it became clear that light could be thought of the same way. Sort of a big question of the early part of the 20th century was, what about space? Is space continuous, where you can just place things anywhere you want in space? Or might space also be discrete? First few decades of the 20th century, most physicists kind of would have said, yeah, space is going to turn out to be discrete. They couldn't make that work. 100 years later, we have managed to make that work. And that's sort of the pivotal realization is, what is the universe made of? In some sense, what the universe is made of, I think, is space. That's sort of all there is in the universe, is the structure of this complicated, discrete space. And so we kind of think of it as they're just a bunch of discrete points. And all we know about those points is kind of how they're related to each other, what the kind of friend network of the atoms of space is. And that, I think, is sort of the underlying infrastructure of our universe. Now that's, in some sense, you can describe it in a very abstract way. It's a bunch of, it's a hypergraph that represents the relations between the atoms of space. But it's what we're living in. And we are part of that hypergraph that corresponds to all these relations between atoms of space. And so our sort of reality comes from sort of our, as entities embedded in that thing, how do we perceive the rest of the thing? And that's kind of the story of a lot of what we figured out in physics in recent years. I mean, there's another piece of this rabbit hole. The kind of the deepest point has to do with, okay, you've got this hypergraph, it represents the structure of space. It is kind of continually being rewritten according to certain rules. That rewriting process corresponds to the passage of time. But then the question is, well, what are those rules? How do we know what those rules are? What determines the rules for our universe as opposed to another universe? And the thing that I realized a few years ago is the right way to think about this is that all possible rules are being applied. It's this thing I call the ruliad, which is kind of the entangled limit of all possible computational processes. You say that's a big, complicated, very messy thing. And yes, it is. But the thing that's interesting about it, it is a unique thing. It is, if you have the idea of computation, then this thing represents all possible computational processes, and there's only one of it. It's this thing that sort of is the encapsulated version of all these computational processes. And then the question is, well, in that thing, if we are observers who are embedded in that thing, how do we perceive the thing? How do we perceive what's going on? And so you might say, well, what on earth could we possibly say about that? The thing that is important is we know certain things about the way we are as observers. So, for example, we know that we can only do a bounded amount of computation. We can't go and trace the sort of irreducible computation that happens in the history of the universe. We're limited. We have finite minds. We have finite brains that just can figure out a limited amount of computation. So, and we also know other things about ourselves. For example, one perhaps very surprising thing that we know about ourselves is that we believe we are persistent in time, which at some level is a crazy thing to believe because we're undoubtedly made of different atoms of space at every moment of time. But yet we have this belief that we have this single thread of experience through time. So one of the big surprises is knowing just those two facts, that we are computationally bounded and that we believe we are persistent in time. Those two facts alone seem to be enough to allow us to say that necessarily it will be the case that observers like us with those characteristics, as things embedded within this ruliad, will necessarily observe that the aspects of the ruliad that we perceive correspond to things that correspond to some core laws of physics. So it becomes inevitable that for observers like us, we will perceive certain core laws of physics to be the way they are. Observers different from us would perceive completely different laws of physics. But for observers like us, it becomes inevitable that we'll perceive the laws of physics that we do. I mean, we don't know all the laws of physics. We can say this, I think, for the sort of three sort of very core sort of pillar laws of physics. Maybe I can explain one of them, which is probably the easiest to explain, which is the second law of thermodynamics. So the three big ones are kind of the second law of thermodynamics, which sort of is the foundation of statistical mechanics, general relativity, the foundation of the structure of space-time, and quantum mechanics, sort of the foundation of understanding how microscopic things work. But the second law of thermodynamics, what does it say? Well, it's kind of its big thing that it says is, if you start with a bunch of things like gas molecules that are sort of sitting in a box, and you start them off in some quite orderly way, then chances are those gas molecules very soon thereafter will seem like they're behaving in random ways and that they're bouncing around in some random configuration. That randomness is what allows one to take averages and to say, well, gases behave roughly this way with just pressure and temperature determining how they behave, and not have to say we have to trace every molecule and where it goes to be able to say what happens in a gas. So the question is, well, why do we believe that this sort of microscopic dynamics of molecules leads to this sort of randomization process? Well, the answer is, I think, that this sort of microscopic collisions of molecules is effectively doing an irreducible computation. So this molecular, this dynamics of molecules, it's doing some irreducible computation, but we, as observers of that, don't get to trace all the details of that irreducible computation. We being bounded computational entities, just have to say, well, it looks random to us. We can't decode that irreducible computation. So that's the reason that the second law works. The reason that we say things tend to get more random, entropy tends to increase, is because we are computationally bounded entities looking at this computationally irreducible process, and it then becomes inevitable that we will conclude that we're seeing sort of this randomization going on because we are computationally bounded entities. If we weren't computationally bounded entities, we wouldn't believe in the second law of thermodynamics. So that's kind of a way that works. Now, in a sense, what we're saying in all of these things is we're making this remarkable jump from the abstract to the actual of the way the universe actually is. And the thing to realize is, what do we know about the way anything actually is? What we ultimately know is just what we internally perceive, our internal experience of what's going on. So the question is, well, how do you go from this very abstract thing to our internal experience of what's going on? We can say, well, there are these, atoms of space and all this kind of thing. And we can say, if we were to think about what that abstract system is doing, its internal perception would be the internal perception that we know that we have. I mean, the fact that we, for example, this is getting very philosophical, but the fact that we, for example, believe in objective reality, it's not, why do we think that there is a world out there that has some definite form? All we know is what we internally perceive. But the fact that we believe in some kind of objective reality, I think it has a remarkably social character. That is, we see all these other people out there and they're kind of like us, and we kind of conclude that their internal experience must be kind of like ours. And we all seem to agree about what kind of outside thing would lead to that internal experience. And that's why it's meaningful for us to talk about sort of an objective reality. If there was only one mind in the universe, I don't think it would be terribly meaningful to talk about objective reality. All that would then be meaningful is the perception of that one mind. So it's but I mean, it is sort of philosophically interesting that we can talk about we can even imagine that we can make the jump from the abstract to the sort of reality as it will be perceived by an observer like us. And I think sort of the concept that we might have gotten to the bottom of kind of how we can, what the kind of machine code of the universe is like, and be able to make conclusions from these very abstract kinds of, we're putting in only abstract things and we're getting out conclusions about the world as we perceive it. That's really a new thing. That's something that's never been possible in science before, to have something where you can imagine that you can derive the laws of physics. You can say the laws of physics have to be the way they are because we know that we are observers of the kind we are. That's sort of a new philosophical twist in kind of, I suppose, the metaphysics of how the universe works.
So I just wanted to maybe I'm computationally limited, let's say. So I just wanted to simplify it for people just so that we're all on the same page. I apologize if it's too simplistic, but I feel like the two big concepts here, if I understand correctly, is first of all, understanding who we are, like who are we as observers, where in the universe we're located, and then also understand what the sort of, not even the universe, but the entire nature of reality is. So the reality is the ruliad. It's all the universes and all the laws or whatever. It's everything. And can we think of ourselves as almost like this, like those sandwich toothpicks that go through a sandwich? We're just living on some tiny slice of that ruliad. We're in one universe. We're persistent across time, and we're limited to our ability to our computational capacity. So we're just like that little toothpick that kind of slices through just one particular slither, interacts with just a few different layers of the ruliad, which is everything. And then from there, our intelligence is not the highest ordered thing. It's almost just, what is that toothpick perceived to be valuable to it, and how is it able to sort of compress knowledge? And that's kind of what science is. Like, how do we compress the universe into understanding? How can we get electricity? How can we get this? How can we get that?
Yeah, I think that's right. I mean, just to highlight one point about the toothpick, so to speak. In physical space, we're very used to being just in this one place in physical space. We're sitting on this one planet out in this big universe and so on. That is what we're in one place in physical space. We're also in one place in rulial space. There are many possible sort of slices of the ruliad that we could take. We are taking just one of them. And, one of the things that's important in the formation of objective reality is that we are very close together in rulial space, just as we are very close together in physical space relative to the vastness of the whole physical universe. And that's why, we all kind of agree the night sky looks the way it does, because we're all sitting on the same planet. If we were distributed across the galaxy or whatever, we'd say, no, there isn't a North Star here or there. It's, it's all looking different. It's because we are sort of close together that we agree on the subjective reality.
Very interesting. And so just to follow up. So that's kind of like what we are and what we're observing and kind of what intelligence is from kind of our perspective, I think that helps to understand kind of like the big abstract versus kind of like what we're looking at. Or,
Yeah.
but so I guess my question is, if we're looking at what the ruliad is, I think if I understand correctly, like let's say at any given point when the universe approaches where it can either go direction A or direction B, you're saying both will happen, and there's a sort of a splitting, and the ruliad is sort of like the limit, the
Yes.
sum of everything. Can you maybe unpack that a little bit, please?
Yeah. I mean, so, well, gosh, there's several different things here. So, I mean, the traditional view in classical physics is that definite things happen in the world. You have laws of motion or something that say you throw a stone, it follows a definite trajectory. The big kind of surprise of quantum mechanics 100 years ago was, well, actually, that's not right. Instead, there are many possible paths that get followed, and we only get to say things about the probabilities of the aggregates of those paths. So that was sort of the moment when kind of the idea that definite things happen kind of got exploded. Now, in what I sort of we've realized in understanding fundamental physics is that, yes, there are many threads of history. The important thing is those threads of history both branch and merge. For various technical reasons, people hadn't really internalized this idea that they could merge. They had the
Right.
idea that they could branch, and then they got kind of confused. And the reason, well, it's not too hard to see. It's as soon as you realize the universe is a discrete place, it's not surprising that different branches of history can precisely, can merge precisely. If you believe the universe is a continuous place where, each branch is an exact real number or something, the chances that two branches kind of overlap is zero. But as soon as you realize that the whole thing is discrete, the chances that they overlap are very non-zero. And so the crucial thing is that, yes, the universe is branching and merging, and we are kind of, our minds are branching and merging, and kind of what we perceive in the universe is the result of this kind of branching, merging mind perceiving a branching, merging universe. And the details of how that works, that's the story of quantum mechanics. We know some part of sort of the mathematical detail, how to follow through from that kind of qualitative idea to the details of the actual laws of quantum mechanics. It's still a work in progress to figure out exactly how that all fits together. But that's sort of the basic idea. Now, when it comes to sort of our existence, one of the things that's important is that we are indeed very small compared to the ruliad. We're very small compared to physical space as well. And the fact that we have a coherent view of what happens in the universe, or in the ruliad for that matter, depends on our comparatively small size. In other words, the fact that we say definite things are happening in the world is because at the size we're at, it's sunny here today. It's snowing somewhere else today. But if we were very big, we would just say all these different things are happening. We can't have a coherent statement about what's going on in the world. And it's a more extreme version in the ruliad. If we were extended throughout the ruliad, we would just say, well, everything is happening. We can't say anything definite about what's happening. The fact that we have a definite individual existence is a consequence of the fact that we are very small compared to the whole ruliad. That's a feature. It's not a necessary feature of an observer. It's a feature of an observer like us, that we are very small compared to the totality of everything. And it's kind of as we learn more, in effect, just like we send out our spacecraft and we fill out a bigger region of physical space, as we learn more, we are gradually sort of expanding in rulial space. We're at a microscopic stage with respect to getting across the whole ruliad. Were we to be sort of as big as the whole ruliad, we might be very proud of ourselves, but the problem would be we wouldn't in any sense sort of coherently exist anymore. There wouldn't be any notion of an individual. There wouldn't be anything where it's like, it's us. It's not everything. It's us in particular, so to speak. We wouldn't have this kind of coherent experience and existence that we are so used to as observers of the kind that we are.
Yeah, that's so wild because we would just like blend back into the universe around us. Can I ask you about graph theory? Just thinking about graphs, nodes, edges, sort of atoms and their relationship to the things around them, nodes and their relationships. Is that the best language that you know of right now for describing like the universe's fundamental structure, or what does and does not graphs help you understand about the universe and in your work?
Right. I mean, in the ruliad, there are an infinite number of different representations of the ruliad. The question for making a model of science, something that sort of bridges between the way the universe actually is and what we can understand in our minds, that's sort of a challenge in making this kind of language for describing what's going on. I mean, in my sort of day job, life has all been about making our computational language, Wolfram language, that is a way of representing kind of the world, the aspects of the world that we humans care about in a way that can correspond to something precise, can sort of formalize that in a precise way. But when it comes to kind of models of the universe and so on, it is the case that there are an infinite number of possible different representations. You have to pick one that is a good kind of ergonomic match for human minds. At least for me, this idea of graphs is a good one. It's not the only one. I mean, we could start talking about higher category theory. We can start talking about kind of all sorts of mathematical constructs that people have made. Those are ultimately look like they're equivalent. But the one that's sort of easy to understand is the universe is made of discrete things. Those discrete things are like nodes in a graph. And what you get to say about those discrete things are how they're related to each other. Like in a graph, how you connect a node to other nodes. A hypergraph, a little bit more general, a little bit more convenient to deal with at a kind of formal way. And a hypergraph, instead of a node, instead of edges that connect one node to one other node, in a hypergraph, you can have a relation between any number of nodes. That's a hyperedge. And that's just a convenient way to kind of think about sort of the data structure of the universe, so to speak. Not the only possible way, but a convenient way. I mean, honestly, it's hard enough to even understand what's going on in sort of evolving graphs. But I think it's the best match that I know to how human minds think about things, although it's equivalent to things you can think about in all sorts of very abstract mathematical constructs. I mean, I have to say, I first started thinking about kind of this graphs as an underlying structure for space-time back in the early 1990s, back when people were first talking about virtual reality. And I kind of had this vision that, I would kind of be in this virtual reality environment with this kind of giant spider web, and I would be kind of going through it and trying to understand what was going on and trying to fit this kind of graph thing into my mind. Finally, when work made a lot of progress on our physics project in 2020, VR had advanced a lot, and I finally got to actually experience kind of these hypergraphs in VR. It was completely incomprehensible to me. Not only that, I also got horribly motion sick in about 15 seconds. But
Yeah.
that, so it from the point of view but nevertheless, it's a kind of mathematical structure to use. So for example, one big project that we have right now is to build what we call infrageometry. So ordinary geometry that's been sort of practiced since Euclid has the idea that you have these points that can be placed anywhere in space. And in the end, space, ultimately, any space that one talks about in geometry, if you look at it microscopically enough, is just like the kind of space that Euclid talked about, where you just place points anywhere you want. For what we're doing, that's not what goes on. The very microscopic version of space is this hypergraph with discrete elements and so on. The question is, can you build a geometry that's based on that? And the answer is yes, but nobody's done it. It's a thing where there are a lot of issues about sort of how you generalize notions of geometry to this thing where the microscopic version is a hypergraph. We're just building that now. It's kind of interesting. I'll give you an example of an issue. An issue is we're used to the idea that space of the kind that we can experience has an integer number of dimensions, like 3, for example, for typical space that we have. The space that comes about from these kind of hypergraphs and so on has no reason to have an integer number of dimensions. And it in fact has dimension becomes this dynamical parameter that can actually change through physical space and in the kind of through time in the universe. It becomes something where you can say space isn't really three-dimensional, it's 3.01 dimensional in some places, let's say. And then there's all kinds of questions about how curvature in space works. That's very integral to the way that general relativity and gravity works. Sort of thinking about how curvature works in 3.01 dimensional space basically is something that is completely virgin territory as far as mathematics is concerned. That's something we have to build. It's kind of a piece of heavy lifting, kind of, in a sense, abstract technology that has to be built to be able to understand how things work in models like these.
So, earlier you mentioned quantum mechanics and the theory of relativity, and they do both seem to fit very naturally, very easily within your theory of everything. So, for example, if I understand correctly, like with quantum entanglement, the spooky action at a distance, which we perceived as weird. We're like, that's not how things are supposed to work. But, in this idea of the ruliad, if two universes split, there might be some sort of a connection between them. That could be that quantum thing that we're talking about. And same thing with the theory of relativity. Like gravity is just the way that the sort of like the space is curved. Can we maybe touch on that a little bit? Like, how do those things sort of integrate within what you're talking about?
Okay, so I mean, it's interesting. You're asking a lot of things where you're, in the end, something like general relativity is a very mathematically defined theory. R mu nu minus a half r, g mu nu equals 8 pi t mu nu. That's Einstein's equations. It's a mathematical thing. Now, so what I'm kind of doing here is I'm kind of describing the qualitative picture of what ultimately grounds itself in this very formal kind of structure. But yes, you can. One thing that's really neat and a surprise to me is that you can talk about a bunch of the phenomena of, for example, general relativity at a qualitative level in these models and get some idea of what's going on. So let's see. Well, okay, things the gets kind of complicated kind of quickly, but let's
If
try
I
and talk
may,
about gravity.
if I may just say this, if you don't think this goes towards the thing that our audience should be seeing, if it's the wrong path that I'm taking, let me know, because I might just not
No,
be seeing the whole picture. So,
this is I, it's just a challenge, okay? I
okay,
like
great. Okay, gotcha.
but I'm also trying to make the point that I'm going to give some qualitative description, and if it's like if you're a physicist who knows Einstein's equations and so on, this is kind of the qualitative version. There's a much more sort of grounded formal version that there's hundreds of pages to read about. But so let's talk about some of the phenomena of relativity. So in special relativity, one of the interesting phenomena is time dilation. When things go fast, time effectively slows down. And one of the things that's interesting in our models is that phenomenon you can kind of understand qualitatively. Let's talk about that. So if the progress of time we think of as being this progress of the rewriting of the hypergraph, it's a computational process. Let's say you have a thing. It's a particle. It's a black hole. I don't know what it is. It's a thing that's a structure in this hypergraph. And it is progressing through time by being progressively rewritten. And that progression through time is taking a certain computational effort. There are a number of computational, there are computational steps that are being followed that correspond to the progress of time for that thing. Okay, now let's imagine the thing is moving. Motion is a complicated thing because when something moves, what we're saying is that thing is getting recreated at a different place in this hypergraph. And it takes sort of computational effort to recreate the thing at a different place in the hypergraph. And so then the question is, well, if you've got a certain amount of computation, the certain sort of budget for computation, a certain number of steps of computation that are going on in the universe, you might have a choice. You can either say, I'm going to use that computation budget to progress through time where I am, or I'm going to use some of that computation budget to recreate myself at a different place in space. So if I am recreating myself in a different place in space because I'm moving, that means I have less computation budget to progress through time. So in effect, time goes slower for me. And that is the qualitative understanding of time dilation. Sort of remarkable to me that there's such a mechanical way to understand that phenomenon, which in the past had just been a mathematical kind of observation about kind of the mathematical structure of space-time in special relativity. Now, similarly, when it comes to gravity, for example, one of the things that, so one of the features, what is gravity? Gravity is, well, so if you just have a thing that's moving through space, it just goes in a straight line. It goes on a shortest path, and that shortest path is a straight line. And that's sort of how things naturally move. What gravity is the deflection of that shortest path in the presence of mass or energy, energy momentum, whatever. And so then the question in our models is, well, what is energy momentum? And it turns out that energy momentum in bulk is effectively the density of activity in this hypergraph. So if the hypergraph is, if there are lots of rewrites happening and there's a high density of those rewrites, that corresponds to a region of space-time that has a high energy density. And then it turns out that this question of what are these shortest paths end up getting deflected by the presence of this activity in the network. And that's something that you can talk about without ever introducing, without, there's sort of no physics to it. It's just a matter of the way that rewriting of hypergraphs works and the fact that this density rewriting is higher in one place and so on. And so that gives one essentially the derivation of the phenomenon of gravity. And the more formally, it gives one kind of what happens in the Einstein equation. So roughly what's going on is this. If you look at fluid dynamics, you've got a bunch of molecules bouncing around. You say, well, what's the aggregate effect of all those molecules bouncing around? Well, you can describe it just by saying, overall, the fluid has some density, it has some velocity. You can describe it according to the large-scale laws of fluid mechanics. So you go from the microscopic molecular dynamics to these large-scale laws of fluid mechanics. And that's the thing you derive for fluids. So now the question is, when you've got this microscopic hypergraph and you've got all these rewriting processes happening, what are the large-scale equations that describe what's going on there? And the answer is those equations are the Einstein equations, which give you the structure of space-time. So in other words, it's kind of the analog of how you go from molecular dynamics to fluid mechanics. You're going from microscopic structure of things happening in the hypergraph to kind of the overall structure of space-time. I mean, that's the rough story. Now, I mean, endless details here. And, the thing that is one of the big questions is, in 100 years ago, sort of one of the discoveries was you can see features of matter that reveal its discreteness, things like Brownian motion. Under a microscope, you can see little pollen grains being kicked around discretely by molecules of water. That was a thing people were lucky enough. Molecules are big enough that you can see that with the microscopes people had around 1900. Actually, it was first discovered in the 1820s. But people didn't know what it was at that time. But so now the question is, well, can we see the discreteness of space? Is there some experiment? Is there some clever experiment we could do that will reveal the discreteness of space? That's something I'm very interested in. I don't know the answer yet. Are we going to be lucky enough that in our times that the numbers are going to work out so that, and we're going to be clever enough in the experiment to be able to see the discreteness of space, to see below the kind of structure, the continuous structure of space. I have one guess, actually, which we'll see how it pans out. It reflects actually the history of physics a bit. Back in the 1800s, people were wondering, what is heat? And people said, heat flows from one thing to another. What flows? Oh, it must be a fluid. So then people invented the idea of caloric fluid, from which we have calories and everything else. And people said, well, heat is a fluid. Well, that turned out to be wrong. Heat isn't a fluid. Heat is the microscopic structure of matter, is the result of the microscopic structure of matter. Heat is the little motions, the kinetic energy, temperature is related to the kinetic energy of molecules in a material. So in other words, heat turns out to be a feature of the microscopic structure of matter. So now the question is, what is the macroscopic manifestation of the microscopic structure of space-time? We don't know. I have a slight guess that dark matter will turn out to be the macroscopic manifestation of the microscopic structure of space-time, which will be kind of ironic because sort of since sort of the phenomenon of dark matter was first sort of imagined nearly 100 years ago now, more recently it got called dark matter, and quite possibly the big mistake is it's not matter at all. It's a feature of the structure of space. Just like caloric fluid wasn't a fluid at all, it was a feature of the microscopic structure of matter. So that's the kind of thing that that's sort of a future attraction of this kind of way of thinking about things.
So I so wanted to move on to talk about like the nature of intelligence, but now I have to ask, like, does it seem like there's any experiment that you can think of that might help us discover an atom of space? And if your team happens to do it, do you have a name? What would you name it if you discover it?
We're kind of chasing lots of different things about sort of the, uh, patterns of noise and gravitational radiation from fast rotating black holes. Unfortunately, hard to measure. Possibly features of the limitations of quantum computing. That's one that's much easier to measure if if the engineering limits are close to physical limits. We don't know. Features of things like dark matter. The sort of the intermediately good case is we figure out some experiment which only costs $20 billion to do, and then maybe we get to do it. The worst case is we realize, we think there's an experiment, but it's centuries in the future in terms of the progression of engineering and technology, right? The very best case is we realize there's an experiment that was already done that we can now understand what it saw, and we realize that's a feature of the discreteness of space. That's the best case. That could have happened with the discreteness of matter. Robert Brown discovered Brownian motion in 1827, but people didn't know what it was. And it took until 1900 for people to realize, oh, actually, that phenomenon, and took other experiments being done with black body radiation and things like this to be able to sort of come up with and other features of viscosity of gases and things like that and so on, to be able to make that connection. If we're lucky, maybe as I trawl around kind of the literature of all of physics and so on with LLMs and things like that, some LLM will sort of show me, thematically these things that we're looking for. By the way, there was this obscure paper that was written, in 1972, where people didn't really understand what the results meant, and they kind of hid it because they thought, this experiment can't possibly be right. And that will turn out to be the sort of smoking gun, the clue to the sort of understand the discreteness of space. If we're lucky, that's how it will play out. I don't know how it will play out. If we're intermediately lucky, it's only a few tens of billions of dollars, and then we can do the experiment that will figure out how this works. But I just don't know. We could be lucky enough. I don't think that an experiment that hasn't yet been done, I'll be amazed if it's sort of only a few $1 million experiment that one needs to do. It'll be some complicated experiment in astrophysics that requires, spacecraft and this and that and the other. My guess is.
Yeah, interesting. Yeah, well, we'll see. Okay, so let's talk about intelligence for a second. I've seen some great papers, blogs that you've put together, kind of dissecting early GPT models and really explaining how they work. So now that you're seeing AI models get larger, they're becoming connected in more ways. There's some new architectures out there that seem more and more capable. We get plenty of stories of surprising emergent properties. What's your intuition about like what we're going to live through in terms of AGI, ASI, computational intelligence?
I think it's a little bit, I don't think it's going to be quite as dramatic as one might imagine. I mean, the history of machine learning has been a history of kind of new modalities finally get cracked and get to be done at sort of human-like ways. So, back 2012 or whatever, image recognition, cracked. A little bit later, speech to text cracked. the big surprise nobody expected of ChatGPT was sort of the generation of text, and kind of this idea that you could, people knew about language models forever, but the idea that you could give it a prompt and it would write a whole essay that would be sort of the answer to the prompt, nobody thought that was going to work. And it does. Now, that probably is telling us that that problem is in some formal sense much simpler than we expected. We thought that was an amazing thing that only human brains can do, but actually it's working through a process that is not that complicated. I mean, my expectation is, and we still don't know the details of this, we've known forever that human language can be thought of as constructed with some kind of syntactic grammar. In English, sentences go noun, verb, noun. But what we don't know is which nouns, which verbs, which nouns. It's kind of like, well, the structure is noun, verb, noun, but it's like, there's certain noun, verb, noun combinations that are never going to occur. They don't mean anything. So I think what in a sense got discovered by ChatGPT through its training and so on was there are these sort of patterns of which noun, verb, noun, and those patterns continue much further. And it turns out that you can do quite long, meaningful things by just fitting together those patterns that can be extrapolated from what you can learn from, the web and the other training data. And I think, what we're seeing operationally, technologically, is we're seeing, we got large language models, and they do certain kinds of things. They're a great linguistic interface mechanism. And then the main thing we're seeing in kind of what's happened subsequent to that in the last 3 years or so is more and more harnesses around this kind of core technology. I mean, the way I see it is, it's kind of like the discovery of the horse. We discovered a wild horse, and the wild horse has certain characteristics. But the real value comes when we attach the horse to a plow, we attach the horse to a carriage, we figure out how to make use of the wild horse capabilities. I think that's kind of what we're seeing as we start to sort of develop from sort of the raw kind of the raw linguistic capabilities of ChatGPT and so on. I mean, the other piece of this is the thing that, if ChatGPT had been invented in the 1600s, we might have a different picture in the developments of science. But the fact is, from the 1600s to today, a lot of kind of formal science got developed. A lot of kind of the idea of mathematics, computation, and so on. We built a lot of stuff that allows us to do things that are far beyond what human minds can do. I mean, when we, every day, I'm computing things with Wolfram language that are ridiculously beyond what I as an unaided human could do. And we're building with computation these kind of towers of formal structure that are not what mind-like things like ours do. And so what we see in kind of what's happened with neural nets and large language models and so on, they do things that are mind-like things, human mind-like things, but they don't do these kind of big towers of computation. I mean, a large part of my technological life has consisted of building systems that can do those big towers of sort of computational things. And I think what we're seeing now is sort of the value of what I might call foundational tools connected to foundational models. I mean, essentially, I view Wolfram language as kind of the foundational tool that encapsulates all of this sort of computational ability. And that's the thing, it's just in a different direction from what an LLM or a neural net does. I mean, a neural net is something that is good at kind of broad but shallow kinds of things. A computational system is good at deep but less broad kinds of things. It's something where you formalize what's going on, but now you can build this very tall tower and the tower doesn't fall over. Whereas what you're doing in kind of a neural net, an LLM, is you can deal with all these different kinds of things, but you can't build the tower very high. I mean, it's kind of like what I was saying earlier on about kind of building stone walls. It's kind of like what the neural net is doing is it's using these lumps of irreducible computation that it's managed to fit together to build this wall. If you try and build that wall really, really high, the fact that there are all these random lumps is going to eventually bite you. So it's a different kind of phenomenon. I think technologically, what I expect to see is kind of the merger of sort of foundational models at the LLM level with foundational tools which make use of computation. And I guess I've been the main one building such tools for the last 45 years or so. So that's kind of on me to make that kind of merger happen. But that's, I think, that's a piece of kind of the future of what we're seeing. I think the value of kind of what we see in LLMs, neural nets, and so on, a lot of the value is these harnesses, figuring out how do we make use of the wild horse to do different kinds of things. Now, there will be more wild horses discovered. There'll be, wild elephants discovered and so on as well. And those different creatures will, I suspect, be mostly associated with different modalities. So I fully expect that robotics will get solved as a kind of a piece of, another modality, just like we've solved language, we've solved image recognition, we've solved speech, well, both understanding and generation. We solve image generation. We solve the different kinds of modalities, which are the things that sort of relate to the things that we know how to do as humans. When you say, what is the general thing? What's the general arbitrary computation, the general arbitrary thing that you can do? Well, it's general computation. It's the story of the ruliad and so on. And the thing is that general computation is very non-human. It's very alien. It's like you can do general computation. We can do that. We can jump out anywhere we want in the ruliad. We can start running it on our computers. We can say, this is what happens there. But we'll look at it and we'll say, this is a very alien thing. We don't care about it. It's not, human-like images. It's not speech sounds. It's not things that we humans care about. It's just arbitrary alien computation. And that's, in a sense, what I think we have, the issue, the thing that is, what is technology? Technology is taking what is out there in the natural world and kind of constraining it, harnessing it for human purposes. That's the kind of thing we care about. And that's, I think, the big story is sort of there's an infinite ocean of computational possibility. What we are doing, what we have to do is just sort of scoop up this in a sense, mine. I don't think you mine oceans very well, but we're kind of mining some particular seam of capability in that kind of whole computational universe of possibilities. And I think that's sort of now, the thing to realize is the abstract AI is doing arbitrary computation. It's doing things that are computational. It can run all kinds of computations and so on. Most of those computations are not things we care about. Increasingly, as that is what is happening, there's kind of a civilization of the AIs that's going off and just doing its own thing. There are aspects of that are aligned with what we care about. We're going to say that's a very important thing. And there are aspects that are just going off and doing their own thing. Now, you might say, what does it feel like to have this kind of civilization of the AIs just going off and doing their own computational thing? Wouldn't that be weird to have that be going on around us? But we have to realize we're completely used to that because that's what's happening in nature. Nature is doing all this computation that is just happening around us, and certain aspects of us we happen to interact with, certain aspects matter to us. Occasionally nature will, make a hurricane and that will cause us trouble. Other times nature will sort of follow things that we know how to deal with technologically and so on. I think it's the same kind of thing with kind of the abstract civilization of the AIs. I mean, I think that's and sort of what we're doing is we're harnessing a piece of the computational universe, just as we're harnessing pieces of the physical universe to do the things that we're interested in doing.
Every time there's so many things that I branching things that I don't want to go down. So I apologize. I have to pick just one to go down. But you were saying how, AIs plus harness, that's kind of where we get a lot of this capabilities from. Now we could see large language models accelerating science just because it might be easier to publish papers that, maybe just publish more papers and maybe, like you said, go through all the past discoveries and maybe find some connections. So I think that would not be too surprising. But if we imagine a time where these LLMs, neural networks, they scale up 10, 100, 1,000 fold, and we figure out how to combine them with the harnesses, you mentioned the Wolfram language, Wolfram Alpha, whatever harness there is to do the symbolic logic, whatever you think is going to work. Project that forward 20, 30 years. Do you think it's realistic for something like the LLM combined with these harnesses to dramatically accelerate brand new scientific discovery? Is that feasible,
You know,
possible?
I've been living the AI dream for 40 years. What does that mean? You know, I've tried to build tools that go from an idea that I have to the implementation of that idea as automatically as possible. And one of the things I've done a lot is to explore this computational universe of possibilities. In other words, I'm kind of leveraging what computation makes possible. And it's kind of like what one hopes to do with AI. That is, I have some germ of an idea. I want to go in this direction. And then I've been trying to automate and been rather successful at doing that, how to make those discoveries, but in a very sort of in an automated way. And I've discovered a ton of stuff. And, you know, there's things like our physics project and so on. That's a consequence of doing computer experiments that are essentially doing exactly this kind of thing. Yes, there is an immense amount of science to be discovered this way. It has rather little to do with the precise, with the technical details of modern LLMs and so on. It is the kind of unfettered use of computation in science. Most of what's been done with computation in science, including with tools I built, is people sort of already know how the science works, and then they're kind of doing the details with the tools, so to speak. What I've spent a lot of time doing is saying, no, we don't know how the science works. Let's just go out and explore in the computational universe and sort of discover things that we didn't imagine were there. That's what I've been doing for the last 45 years, basically. It works really well. I mean, some number of people have been doing this now. You know, now we kind of call the field ruliology, the study of simple rules and what they do. And there are an increasing number of people who do that. Some people have been doing that since the 1980s. But it's, you know, that's what it looks like to be able to make discoveries kind of in the computational universe. It's incredibly rich and fertile. You know, we know some methods for doing these things. I've tried to develop those methods. There's vastly more that can be done. To what extent can things like LLMs help? I don't know. I mean, I've done lots of experiments. I would say the number one area where they help is thematic searching of what's already known.
Hmm.
In other words, it's not, you know, the thing about do a computational experiment, discover something that's never been discovered before. That's a computation story. That's not an LLM story. That's, you know, in the end, it's kind of like I can generate sort of, if I'm trying to enumerate possibilities, I'm just going to do that with computation. I'm not going to tell the LLM, go try all these different possibilities. It's an unbelievably inefficient way to do that. It's but what I can ask the LLM is, hey, does this look like anything that somebody wrote in a paper, you know, something about 30 years ago? It might know that. It might be able to sort of statistically connect what I'm now doing to what was there in the past. And that's, I think, you know, a very useful thing, that we can make use of kind of the corpus of human knowledge about science and leverage that in a way that we haven't been able to do before. Now, you know, it is a progression, because the fact is, when I started doing science in the 1970s, you know, there were the first computer abstracting services. You know, you could log in to some time-shared system and you could do keyword searches and find papers that were about this and that thing. There were even paper versions of the Science Citation Index. You'd go through and find things that way. Vastly less efficient than what you could do with web searches and so on, which is still, again, less efficient than what you can do with kind of thematic searching with LLMs. But it's not kind of a night and day difference. It's a matter of, it's a quantitative change, which may lead to qualitative results. And again, you know, I haven't yet been successful in finding, for example, if it turns out that I find something which allows us to understand the discreteness of space from some experiment that happened to get done in the 1970s or something, that's going to be a big win. And that's going to be something that probably couldn't have been done without kind of this sort of ability to thematically search things. So that's an example. When it comes to people, it's like, oh, you know, we're going to discover these new mathematical theorems and so on this way. It's, you know, no, it's not the way this, you know, there's a lot of detail behind that. But I think the thing, I mean, it's a little bit funny because people have been going and trying to find, you know, is there a nail that the hammer that we have, you know, is there some nail? Can we find some nail somewhere that's some kind of mathematical theorem that's been pretty obscure that people didn't solve because nobody cared often?
Right.
And, you know, with our hammer, we can now solve it. And I think that's, you know, that's not the more interesting thing. I mean, I think the thing that So, what I would fully expect is that the routine integration of all existing human knowledge into the next step becomes something that is a routinely done thing. Now, already some of that happened. I mean, the existence of the web did some of that. But this is another big step there, where sort of at every moment you can leverage everything that is already known. Not quite the same thing. And then the thing that, in my view, is even more powerful, but a methodology still not that well understood, is the methodology of going out into the computational universe and doing, it's like saying, let's go into the natural world and let's go look for all these different creatures. Let's go turn a telescope to the sky and see what's out there. We're still at an early stage. I'm 45 years into doing that in the computational universe. We made a decent amount of progress, but there's vastly more to explore. And I think that's the place where there is the really, really vast amount of leverage that still is to come. And, I don't, that's not so directly related. It is something that kind of the wake-up call of computation can be important in making progress in science. Maybe that's something that comes from the current world of AI and LLMs. But I think that the really big leverage comes from this kind of understanding sort of this computational paradigm and really being able to use it in to discover new science.
Yeah, that's cool. It's like probably more fun for you to go out there and look for more wild elephants than it is just to stand even higher on the shoulders of the people we already have.
Yeah, but
Yeah.
it's yes, it's the I have to say I often analogize kind of exploring the computational universe with sort of discovering these computational animals, and it's kind of a remarkable personal thing in a sense that I do all these experiments. I've been doing them for 45 years or more now, and you do these experiments and you imagine what's going to come out. Then you do the experiment and it always surprises you. The computational animals are always smarter than we are. It's kind of like you thought you knew what was going to happen, but you don't. And this is it's a kind of a feature, a sort of a humility in doing science that is actually not typical of most of science. In most of science, it's kind of like we kind of know what's going to happen, and we're filling in details, so to speak. This is a place where you really get to sort of explore the unknown, and it's kind of exciting. It's also challenging because you kind of have to deal with the unexpected is not so easy. It's much easier if you kind of know what's going to happen, and I use this analysis method and this is going to happen. It's more challenging if you don't.
Yeah, I'm guessing you're kind of addicted to the thrill of the chase.
Well, yes, it's a lot of fun. I mean, look, I mean, I'm spoiled. I'm completely spoiled because the fact is the things we've discovered are, absurdly powerful. And, the thing is that, a lot of these problems, okay, so the big picture, I think, as I've understood in the last few years, is a lot of progress in science got made about 100 years ago. And what happened at that time is people understood how to formalize things in mathematics, to some extent in physics, to some extent in biology. It's kind of like people built formal structures. And then that sort of propagated for a while. Some of those formal structures got stuck on things like Gödel's theorem and so on. But then that notion of formal structures led us to computation. What we can now do is think about those formal structures in bulk. That's kind of the story of all of this ruliad stuff and computational reducibility and so on. We're taking kind of the next step with formal structures, not just look at each one on its own, but what is the bulk story of these things? And the thing that's kind of, it's a spoiling discovery is that realization, that kind of paradigmatic approach looks like it is able to crack a whole series of things that have been kind of stuck for 100 years. I mean, the question of, how fundamental physics works, questions about the foundations of mathematics, questions about the foundations of biology, questions about foundations of computer science, and so on. It's it's a crazy thing. And I would never have expected it. Honestly, this was not my kind of expected life plan, so to speak. I mean, I've been doing science and technology. I'm pretty happy with science I've done and the technology I've built and so on. But the fact that, about 6 years ago now, with these breakthroughs in our physics project, I realized, oh my gosh, there's this whole paradigm that allows us to go and, tackle all of these different, really pretty major problems. And it's, as I say, I'm totally spoiled, because it's kind of like, I was just working on the P versus NP problem, which is kind of a classic problem. And I made a bunch of progress. And it's like, that's crazy. You shouldn't be able to do that. This is a problem that's been around for 50 years or so. And there's been, I haven't solved it, but at least there's a kind of some concrete progress that one can see one's made, and one's being able to frame the problem in a different way and so on. And it's sort of crazy that it's possible to do something like that in, with this paradigm. But I'm addicted. It's very exciting. And it's kind of almost sort of unfair, because there's so much low hanging fruit, I think, to pick, that it's kind of like, I got to pick all of this stuff. And
Right.
I also have a company to run, and technology that happens to be very, very relevant to today's world. And so it's a personally challenging thing to kind of, to deal with all the low hanging fruit and all of the technology and things like this.
Absolutely. And it's such a fascinating, it's such a great position also, I feel like, to be in as an academic, to also have the businesses that can fund the research. It's it seems like such a great sort of position to be in, to just do pure research. So just in terms of, you mentioned some discoveries in the last 6 years. So if that's something very interesting, we can dive into that. I also have some other questions about, the inference geometry that you talked about, and and a lot of other stuff, and also AlphaFold and Google DeepMind. Which one seems like the most interesting one for you?
Boy. Well, I mean, a lot of the things I've been talking about, the ruliad is a thing from 2021. The physics project, the hypergraphs, all that kind of thing, that's from 2019 and 2020. The stuff about, foundations of biological evolution, that's from 2024. The stuff about machine learning, 2024 or 2025. These are the stuff about P versus NP, that's 3 weeks ago.
7, yeah. It's
Wow.
like be
Wow.
next year.
So I mean, this is things are kind of, I made a bunch of progress in understanding things about the foundations of biology. That's from about 2 months ago. I
Wow.
mean, there's things happening in a very very kind of immediate fashion. It's kind of, the other thing that we sort of touched on a little bit is the implications of all of this for philosophy. From a personal point of view, my mother was a philosophy professor, and when I was a kid, one of the things I would say is, there's one thing I'll never do when I'm grown up, it's do philosophy. But here I am.
It's too fun.
I've been kind of forced into it, because a lot of the science that I've done is, really tells one things about metaphysics and so on. And I think we really made a lot of progress there. And it's been kind of interesting to me to see a bunch of philosophers be really interested in this and make a lot of connections that span many centuries of history about the things that we're saying now, and how those kind of resonate with things that people kind of partly figured out, a long time ago. And that's another kind of interesting direction. I think in terms of, I don't know, I don't have, if we talk about things like proteins and so on, I can say a few things about that. I mean, one of the things that make progress on recently is the following question. What is biological tissue like? You do some experiment that I'm too squeamish to do, and open up some creature and see what's inside. Um, and, what is it? Is it a liquid where there are a bunch of molecules randomly bouncing around? No, it's not. It's some complicated thing that is some sort of bulk orchestration of molecules. Very little of what happens in us biological organisms is just molecules randomly bouncing around. It's mostly these very complicated sort of chains of things where some enzyme interacts with this and binds to that and does this and that thing. So the question is there some overarching theory of how sort of biology, this bulk orchestration of biology works? And one of the surprises of now 2 months ago or something was, yes, there does seem to be a theory that you can start to make of that. And it's a thing I call the rulial ensemble. Here's the basic idea. So we talked about things like fluid dynamics. When molecules are randomly bouncing around, the sort of aggregate behavior is we get from the laws of fluid mechanics. The question is, when you have rules for a system which sort of on a large scale satisfy some fitness criterion, like they make the creature live long and prosper, what consequence does that have for the microscopic structure of what's going on? It's not obvious it would have any consequence, but it turns out that as soon as you have a computationally bounded overall fitness function, that has consequences for the microscopic structure, and it leads to what I call mechanoidal behavior, things where there is sort of small-scale mechanism, which is, I think, sort of a key feature of kind of giving one the beginnings of sort of a theory of how biology works. Because we haven't really had a theory. In biology, the best we can say is, well, it is that way because that makes the whole organism fit and not die. But that doesn't tell us the details of why kind of, it doesn't sort of start talking about sort of the whole orchestration of molecular processes. I think we're beginning to have sort of a theory of that. It's going to be something that has a very different character. We've had theories in physics which are based on mathematics, for example. That's been a successful approach in physics. We're beginning to have this kind of sort of the raw material to make theories in biology. And I think that's a coming attraction. I also have a strong suspicion that we will have ways to make theories in economics that also work in this kind of way. Haven't done that yet. I've been I've been wanting to do that for decades, and we're slowly edging towards being able to do that and sort of understanding what is the raw material from which we can make theories there. Because it's like in physics, we had things like calculus, which gave us the raw material to make theories. But we don't have that raw material in biology. Calculus does rather little in biology, for example. We need a different kind of foundational approach, and I think we're beginning to get that for biology.
Okay, so very interesting stuff. My final question for you might be somewhat unanswerable, or maybe you'll have to answer it in sort of a philosophical way, but it seems like throughout your career, you've done so much like stepping back, like moving from small to big, to asking like, how does the pieces come together to the whole? What is different? And you keep kind of moving back and back and back, and you get this entire universe, this whole ruliad, maybe something I can imagine as a graph. Does it ever give you any insight into the question of why something and not nothing? It always seems to me like there just should be nothing. Like the fundamentals of energy,
Right.
like
Well,
why is something not nothing at the highest level?
I think we have some idea of that now. I mean, look, just to talk about my kind of process in my life. I mean, I've been interested in kind of the foundations of things. And honestly, what has made that possible is sort of increasing confidence to kind of say, let's unpack this thing at a foundational level. I mean, I started when I was a kid doing particle physics. I was quite successful at that. That kind of, I started building technology. That worked out well. It's been kind of a building a tower of sort of technological and scientific, concepts. Plus, frankly, the confidence to say, look, I'm going to go look at the P versus NP problem. I know people have looked at that for 50 years, but by golly, I might actually make some progress, and let's go do it. And so that's been an important thing for me to sort of have the confidence to actually address the foundations of things. And it's turned out, it's often the case that in fields, there are foundations that get built, then people go another 50 or 100 years, and then nobody's looking at those foundations anymore. And sort of the ambient discoveries that have been made, ambient kind of paradigms, some cases things I've spent a lot of time developing, allow you to then start talking about those sort of underlying foundations in a way that nobody bothered to look at, because they said those foundations, they were 50 or 100 years in the past. We don't think there's anything to do with them anymore, and we don't kind of have the confidence to unpack those. Now, in the question of why there's something rather than nothing, I think we have an understanding of that, actually, which is quite surprising to me. So let's talk about the ruliad. And let's kind of compare that to other abstract kinds of things. It's like 2 + 2 = 4. You could instantiate 2 + 2 = 4 as I have, 2 rocks, 2 lots of 2 rocks, and I put them together and I have 4 rocks. But we know that 2 + 2 = 4 is something which we can discuss abstractly. We don't have to have rocks to talk about numbers. We can talk about numbers in a purely abstract way. That's a thing which is sort of a necessary feature once we've defined the notion of numbers and defined the notion of plus and so on. Inevitably, 2 + 2 = 4 is abstractly the case. So the thing to understand about the ruliad abstractly has to be the way it is. It's not a matter of an actuality of atoms of space or anything like that. It's just an abstract thing, like 2 + 2 = 4. It has to be that way. It's not a thing which you have to instantiate in any way. Now the question is, why is there, once there is this necessary thing, why is that, within that necessary thing, there may be entities like us, which are parts of that necessary thing. What is not obvious is why entities like us should exist.
Mm-hmm.
Once the fact that there is that necessary thing, then within that necessary thing, there are entities like us. Once there are entities like us, the perception that entities like us will have of what's going on is that there is a reality out there that corresponds to this necessary thing. So the scientific thing you have to prove is, why are there entities like us? Is it inevitable that in the ruliad there must emerge entities like us? That's a thing that I think there is a serious chance that there are scientific things to say about. So, for example, one of the things that is surprisingly mundane is, the fact that there are lots of us. I mentioned before why the fact that there are lots of us is important to the sort of formation of an objective reality. It's the fact that there are lots of us depends on kind of the fact that self-reproduction works in biological life. Something that seems very mundane and something that seems very, that the existence of the universe can't depend on something as mundane as that, you might think. But the fact is, the overall existence of the ruliad is not a thing about which there is any, there's no choice about that. It is a necessary object. The thing that the thing that we don't know is why do we perceive the universe from inside us? And it's sort of because we happen to be where we are. It's not something derivable. It's not like we can derive why are we on this planet rather than another one. It's, well, we are here, and that's the way it is. Now, there is a certain amount that we can expect to derive. So, for example, I realized that things like the origin of life, and I think this sort of abstract definition of life, which I'd never really understood until very recently, is related to this kind of bulk orchestration of molecular processes, this kind of technology stack of features that leads to life as it is today. And I think that does that necessarily occur in the ruliad, and how often does it occur? These are things that I can imagine us being able to derive. And I can imagine us being able to say sort of things like that will inevitably occur. Now, so that's, and then the notion that sort of there's this necessary object, and within that necessary object is an observer like us necessarily there. And to an observer like us, from inside the observer like us, there is an actualization of this necessary object. So I think what we're kind of, we are making the jump from the abstract thing to the actualization of that thing with respect to an observer like us. I don't think all those philosophical points are fully nailed down. I think there's a piece of science that is it necessary that observers like us must exist, and so on. We don't quite know that, but I feel like we've got to come a long way to the question of why is there something rather than nothing, there is inevitably something, because there is inevitably this abstract object that is the ruliad. Whether there's anybody to see that inevitable something, that's a different question. But that's a question that is sort of, it is within the what you can imagine being able to scientifically discuss. And that's where I think we're going. And so I feel, I've certainly wondered for a long time, why is there something rather than nothing? I kind of feel like there's something rather than nothing because abstractly it is a necessary thing that things abstractly work in a certain way. So that's my attempt at that sort of ultimate piece of metaphysics. And it's a funny thing when, as one leads one's life and one imagines that we kind of have our arms a little bit around the whole story of everything that is and so on, and the whole kind of story of how our universe is put together, how does that affect sort of how we should lead our lives? I mean, the fact that I think it tells us something, that we're pretty sure the universe is computational all the way down. And so when we think about computation, it really is an important paradigm. It's not something where we say, it's something which applies to computers, but doesn't really apply to anything else. It really is the paradigm of the universe. And so we should take it seriously. Just like, when Copernicus was arguing that, even though you think the Earth is standing still because that's your everyday experience, really take the math seriously because it says you don't have to think about it that way. So now we're in a situation where it's like, take the computation seriously because it's the way the universe is actually built. And I think that's one piece. I think the other piece, which for me is important, is this idea that you can drill down and get to the foundations of things, that it's not that there is a sort of an underlying machine code to things, and that's something in one's everyday life, in running a business, for example. The idea that there are foundational things one can understand, there is a big picture that is foundationally understandable, is something which is important in kind of the leading of one's life. And I kind of think sort of foundational thinking about things is something that, well, not enough of it is done, but that's something that you're kind of led to by this kind of adventure in science, so to speak.
Absolutely. One thing where my mind is just wondering too, and this might be just a yes or no question if you want, because I know we're a little bit low on time. But I mean, a lot of the stuff that we talk about, like you're talking about drilling down to the foundation, you can almost call it a source code. You talked about the computational budget of how fast things move. A lot of this seems to be at least how we're saying it with our like existing language. Like it does have some sort of a design to it, like some entity out there, maybe outside of the ruliad. Is that, that's what I'm asking, is that necessary, or it can exist without that?
It doesn't make sense. The
Interesting.
ruliad is everything that is computationally possible. So in other words, if you say, is there a God that made the ruliad type thing, that doesn't make any sense, because there's sort of no choice. The ruliad is this unique, inevitable, sort of necessary object, and there's no choice about the construction of it. So when you say, is there some entity on the outside, so to speak, it's the entity put in this video game cartridge rather than that video game cartridge. No, there's only one possible video game cartridge that is the everything video game cartridge. And so that doesn't, and I think, it is a confusing thing. I admit that when I talk about computation, one has the idea, because that is a metaphor that comes from our everyday experience of using computers for purposeful objectives and so on. We tend to think of it as sort of a thing that was designed, but that's not the way I think of it. The way I think of it is it's arbitrary rules. It's computation in the wild. It's not computation as sort of harnessed by humans. It's computation which is running these rules, but doing arbitrary kinds of things. So I would say that what we're learning from the whole story of the ruliad and observers in the ruliad and so on, the interesting thing we're learning, I think, is that the universe as it is the way it is to us because we are the way we are. It's a very much of an inward reflection of the way we are, that the universe is the way that it seems to, is the universe as we interpret it is the way that it is. It's not like somebody threw us this particular universe. It's we got this universe because we are the way we are.
Thank you so much.
Thank you.
You've been so generous with your time. Thank you so much. This was one of the greatest conversations. Thank you so much. We're really appreciative. Is there anything you want us to post or mention, or anything else we can do? Whatever you want to say to the world, please.
What would I like to say to the world? I don't know. It's I've been lucky enough to discover some interesting things. The things I've discovered are sort of deep paradigms. I happen to have turned a bunch of those deep paradigms into technology. It's it's a lot of fun exploring the technology in these deep paradigms. Go try and do it. This is a moment in history where we just opened up this sort of huge kind of huge territory with these paradigms, and it's a great time to do it. But these paradigms are deep, and it's something where there's there's effort needed to kind of explore this territory, but it's really worth doing, and it's really fun, and lots of people have started doing it, and it's a great thing to do. And it's sometimes people will say, I discovered all this science and so on, and read what I wrote, and that's all there is to say. I think I can say a little bit more than that, because we built a bunch of technology to actually do these things. And it's not just a, read the words. It's like there's technology that actually lets you do this stuff. And I encourage people to take advantage of that.
Absolutely.
All right.
Thank you so much for your work.
Yeah,
thank you for your time.
so much for your time.
And we're very excited to see what else comes out of this. Thank you. Take care.